So we will continue from where we left off. So we are looking at we just finished looking at the analysis methods. So today we will quickly go over the method for sampling and processing of air. We already covered sampling of water, sampling of soil, processing of soil. We did not do processing of soil, sampling of soil yet. We will do it today, finish that also. But for sampling and processing of air, you may have two sampling objectives. One, in air, you are interested in looking at the composition of the vapor, which means what is the vapor phase composition, concentrations. In other words, we are looking at concentration of different components. Then we are looking at composition of the PM, the particulate matter associated with air. So in this we can look at either the concentration of PM and the composition and the concentration of components of PM. It means you are taking the entire particulate matter as a whole without any specific distinction. It's all particulate matter, and then you also make a distinction that this particulate matter is now composed of what's the composition, elemental composition of the organic composition of the particulate matter itself. So these three things are the objectives for air sampling typically. So these are used for various purposes, for exposure measurements or for transport estimations and so on. So the first so the sampling and analysis method, as with all our cases that we have done, in order to, you need to have the objective first. Based on the objective, your final analysis, which instrument you are using, and you backtrack the entire trajectory of the sampling protocol is developed for that, based on that. So the sampling, you have to decide whether you are sampling for vapor or PM, two things. Yeah. So in PM there are two things. In vapor there is only one, the vapor phase component. What we mean by vapor phase component is in this atmosphere here, I am looking at the composition of benzene vapor only, that is in the vapor phase, pure vapor phase, as against benzene that is adsorbed on particulate matter sitting on this, running around, flying around in the air. So these two distinctions that we make. Okay. So let us start with the PM, because in general when you are sampling air, PM is part of the air. So if you are only looking for vapor, you need to separate the PM out. So that's one. So we will look at the PM part first, and then we will go to the vapor part in the next this thing. So sampling of PM, there is a large set of methods in which are available now. So again, when you say sampling of PM, you have to now we know that PM is classified again as PM10, PM2.5 and a whole bunch of things, and ultrafine particles and so on. So you need to know what is it that you are looking for. Okay. So let us say that you are interested in sampling PM10. So PM10 sampling and measurement. This is an example. So what would you need to do? The general design of PM sampling, PM10 sampling, which means that PM10 as the definition is everything, all PM with less than the aerodynamic diameter of 10 micron, which means there is what is called here, you are classifying. You need a classifier, you need to separate, remove all particles above an aerodynamic diameter of 10 microns, and then you want to measure the rest of it. Okay. So when you say PM concentrations, we are talking about rho 3 1. 3 is a solid, 1 is air. So, rho 3 1 is the mass of solids divided by volume of air. This is M3 divided by V total. V total is V air. That's typically we say V total equals V1 when we are doing this kind of sampling. So, we need to estimate these two for calculating. It is true for everything. For vapor also it is the same kind of definition that we are looking at. So, but here if we say it's PM10, then this M3 must be PM10. If rho 3 is PM10, this M3 must be PM10. So, we must find a way to separate all particles above PM10 and below PM10. So, what is a good way of doing it? A classifier or a separation of PM greater than PM10. You are interested in collecting anything below PM10, above PM10 you don't care. Just so you have to separate it. So, you have any some of you have used it, but those of you who have not used it or those of you who have used it also can give an opinion as to what can be done to separate, on what basis. So, we are talking about aerodynamic diameter. So, the separation is on the basis of aerodynamic diameter. The aerodynamic behavior of the particles, which means that the way the PM is defined, you use the same principles to get rid of it. So, we use what is called as an impactor. An impactor is by very simply the definition of aerodynamic behavior as we looked at from inertial impaction, interception, this is mechanisms we had talked about when we defined PM10. An impactor allows the impact or collection based on inertial impaction, gravity, interception, Brownian motion or electrostatic attraction or something, electrostatic forces. These two are the more important ones. This is the next. Gravity a lot of times does not apply to these kind of situations, but it is important. All of these things can happen in a open environment, but we can engineer the impactor in such a way that we can use one of these things. Okay. So, a PM impactor. So, if let us say you have an impactor. So, what will happen in impactor is, let us say that this is the flow of air and I have an impactor, something, and what goes through the impactor, if this is the impactor, what goes through the impactor, what is retained on the impactor is anything greater than PM10 is retained here, greater than PM10 is retained here, less than PM10 goes through, and then you have to measure it. So, you have various options of measuring it. One of the simplest option of measuring it is by gravimetry. Gravimetry is mass, measuring by the mass of it. So, if you are going to measure the mass, then you have to collect it. Yeah. The easiest way of collecting solid in a fluid is by using a filter. Okay. Just as what we do for total suspended solids. We are sending water, we collect all the particles, we measure the filter paper before and after. So, whatever is collected on the filter paper is the mass of the particulate matter in a given volume of air. So, that is all. So, you have the volumetric flow rate of air, and you have the mass that is collected on this. So, now here we have separated the components, we have separated the impactor will separate whatever you want to separate, and the filter collects the particles and you want to do gravimetry, but you do not have to do gravimetry, you can do anything else. You have another way of measuring particles, you can do that also. Okay. So, the standard, one of the more commonly used, this is evolving. So, whatever I say now may not be applicable 2 years later. So, it is always evolving depending on what you want. But PM10, PM2.5, the methods are fairly well established, and this is we will just go over that once. So, the impactor is typically a device that will impact particles in a flow. Okay. So, one example of an impactor is something that looks like this. So, we will go to the PowerPoint. So, there is an impactor, there is no size segregation. So, you are just doing, you have a filter paper will trap all particles. You have a flow, so you have a flow here, all particles are coming through it, and there is a filter paper, air goes across it, there is a pump. This is general without an impactor. If I just want to take everything, I put a filter paper which will trap all particles. Now, if I have an impactor, there is an impactor here, I put this here, what will happen is particles will go, some large particles will get trapped on the impactor. What it essentially means is the smaller particles, as you can see, tend to go around this thing. So, what we are seeing here is there is a diversion, the flow goes around this impactor. Along with it, this is the same principle what we talked about during impaction. Smaller particles which have larger momentum will not be able to change their trajectory, their momentum is very high, and smaller particles, momentum is smaller, can move around with the air. So, depending on the velocity, depending on the momentum, which means it is a velocity, and very specifically what we call as the stopping distance, there is a stopping distance. This is how speed limits are designed for roads. It is based on stopping distance. If some vehicles come right in front of you, how long does it take for you to stop? So, if you do not stop, you will go and collide, this is impaction. But if your speed is low enough, so you can see something, you can veer off, or you can adjust your flow. So, the stopping distance is very small. So, the design can be made such that the impactor is very close to the entrance or very far away from the entrance. You can adjust the behavior of the particle, trajectory of the particles. So, the aerodynamic trajectory of the particle is designed, and this impactor is designed in such a way that certain size of particles will go around. Okay. So, the impactor, the factors that we are looking at is the flow rate and the geometry of the of this design. These two things are important for the design of an impactor. So, you can have a PM10 impactor, you can have a PM1 impactor, you can have a PM2.5 impactor, whatever. So, this is based on some fluid mechanical, solid mechanics calculation, or by trial and error. You can observe, you need a strong basis for doing that, because this is not easy to first of all figure out which particle has which diameter, aerodynamic diameter. So, the design of this is done using spherical particles of known density. So, you can know exactly on the basis of definition of aerodynamic diameter, we use spherical particles to design this thing, and then this is used to define PM. Okay. So, if you know that based on the definition of aerodynamic diameter, this impactor works for that particular particular size, then it should work for anything that comes through it has an aerodynamic diameter of that size. Okay. So, you have designed it for PM10 and you have tested it with spherical particles of PM10, it should, if it collects particles of any random shape and density, it means that they are all PM10, that is all it means. So, this is the way we calibrate it. Okay. So, these impactors will accumulate particles will accumulate here, and the rest of it will accumulate on the filter paper, and then you take the filter paper and measure it. So, it does this when so this is general design of an impactor. So, impactor can be anything. So, this is in one of the final designs, depending on the flow rate, one of the impactors is a small plate, and there is a plate here and there is an opening in the side, you can see there is a cylinder and there is a nozzle. This nozzle allows flow to come in and air moves around like this, and there is a filter paper here. So, this is held in place. So, if you look at the top view, it will look like this, the impactor will look like this. There is impactor, this is an opening, and this is the impaction surface, if you look it from the top. Okay. So, the air can go all around it, and in the middle. So, the size of these things will change. You can adjust the dimensions of this, you can adjust distance between it. Sometimes what happens is, because the air is going out from the side, the next impactor stage may be something in the middle, the opening may be in the middle, right in the middle. So, that air has to curve and go through in the center. Particles which cannot do that will deposit in the top outer surface, so on. So, all kinds of possibilities exist. Okay. This is one type of impactor. The other type of impactor is a cyclone. A cyclone is a device where the particle, the air and the particle are allowed to impact. The impaction is not a single surface, it is continuously happening. So, this is based on the turning of the fluid, right. So, in the cyclone, the air comes in and it has to go around, round, and then it escapes to the center. So, if you look at it from the top, this is what is happening. Air comes in, and there is a central cylinder and outer cylinder, air goes in and it has to turn. At every point it is turning, particles can, there is a tangential velocity, the particles can go and hit. So, you have a larger residence time, and therefore, you have a larger possibility of particle deposition. So, the longer the particles, we can have a larger classification of particles here, you can have a lot of particles that can be removed based on this. It is a simpler device to design and make. So, cyclone is used. So, in the case of air sampling, you have industrial cyclones, big huge cyclones the size of this room or bigger, which will remove particulate matter from very large power plants and all that. But these ones, you are not sampling much, you are sampling, you are doing very small amount, you are not pulling in million liters of air and all that. So, you are doing small amount, we will come to that. So, these cyclones are very small, they are small as this, sometimes very small, this is the size of a few inches in diameter, 1 inch in diameter, few inches in diameter. They are attached to a sampling system, an impactor. This is an impactor, so this is PM10. So, cyclone design is fairly advanced, so you can so the particles will get collected on the side of this thing, and they will settle down here, because the air that is coming has a certain, if you close this part, there is only one way the air can go, it will go out there. If it is upright, you do not even have to keep it closed, you can keep it open, because the air will naturally tend to go up, so it will escape that way, unless there is a dense gas which is denser, gas that is denser than air, then you have to worry about that. So, all these are operational details, we will not get into that. So, one of the constraints for doing PM measurement is the measurement itself, the filter measurement is gravimetry. So, if you have gravimetry as the measurement, see what we are doing in cyclone and impactors, we are separating it. But this filter you need to measure, this filter is now undergoing gravimetric measurement, which means that the filter has to be weighed, and the amount of particulate matter that is collected on it must be measured. So, what is the constraint for gravimetry here? The same thing what we did in the TSS example. What is the constraint for gravimetry? The minimum mass that you can measure, yeah. And we are talking about particles that are in the micron range, and we already mentioned that in that discussion that micron range particles, the lower you keep going, they do not contribute much to mass. So, if you are going to do gravimetry, what is the other way out? If you are doing gravimetry, you have to sample large volumes big enough so that your mass accumulation is big enough. Okay. So, sampling times which is also called as sampling intervals can be anywhere from 1 hour or 8 hours, 24 hours or longer, and volumes are large. You have very large volumes of air that you are collecting. So, if you have PM is mass by volume. So, if you have very large volumes, so if you are collecting it for shorter duration of time, you can still get a reasonably high amount of mass that you can collect. That is the idea. Yeah. So, because when we report PM, this is again objective of reporting PM. What will you report PM as? Concentration. If you are doing 8-hour sampling, it will give you an 8-hour average. You are not able to say that the concentration is high at this point in time or this point in time. Within 8 hours, say I am doing from 8 o'clock in the morning to 4 in the evening, or 6 in the morning to 2 in the afternoon. It will say that between 6 and 2, the total accumulative mass concentration is this much. It cannot give any finer detail than that. If you are unable to do 8-hour sampling, you do 24-hour sampling, it says the entire daily average is this much. Morning 6 o'clock to next day morning 6 o'clock, this is what I am measuring. So, there is that information is useful for what we call as how will we use this information. If you are able to do only 24-hour average sampling, it is only as good as that. So, when you look at standards, this is the basis for when standards are seen in CPCB's website. If you go and see, you have a 24-hour average standard. What it means is, if I am exposed to a 24-hour standard concentration, and this is a possible health effect that I am, so they will have if you are above this standard, if the concentration of the 24-hour PM10 value is above this, it is likely to be harmful to your health. The reason they are doing it is that if you cannot get less than 24-hour averages, you can't define a standard which is less than that, because this is your measurement tool. So, if I have a tool that can measure round the clock, okay, they will say somebody is outside, they say between 2 and 3 in the afternoon, do not go outside, its concentrations are very high. So, just do not go outside during that time. Rest of the time if you are outside, it does not matter, your average exposure is going to be very, very small. So, your this thing is going to be very small. So, if you look at this kind of things, you have time of the day and the concentration. So, you may have a spike, you may have several spikes and some baseline concentration. You are going to miss all of this if your sampling measurement window is the entire thing. If your measurement window is this full thing, you are going to miss this spikes, you do not know when the spike is. Okay. But the reason these standards are reported like that are because that is what they have, you can't measure in finer resolution for a very large network of samplings. So, as I said, this is all will change, all of this will change, because every year as we go, there will be new developments in the protocols of measurement. You are able to measure it for cheaper, therefore a lot more deployment of PM sampling is done, and therefore you can go to lower and lower. What we would like to have is actual full real time concentration maps, so that you exactly have what information that you need, when are the hot times, spot times, which area is highly polluted and all that. So, we would like to full information so that we can use the information in whichever way you want. Okay. So, these are time average samples, and the standards are based on the protocols for measurement. I think that is why we see in the standards we will see 8-hour or 24-hour average, the numbers are different. So, one of the device that is used for large volume sampling. So, we are looking at gravimetry. Gravimetry means it is 4-digit balance. We are looking at this kind of a balance, 4-digit balance. It is very commonly available. It is not very expensive. It costs anywhere between 40,000 to a lakh, maybe, depending on the range of what you are using. For that, then it is easier for one measurement to be made. So, one of the goals of this kind of ambient measurement is you must have as many measurements as possible. It must be easily accessible, people must be able to afford it. You can't have a 60 lakh equipment to do PM measurement, nobody will do it, it will be sitting there. So, you have to have cheaper methods of doing it, but when you have cheaper method of doing it, you are obviously going to have loss of information. So, a PM sampler is high volume sampler, you can use measurement, you can measure it using a balance, 4-digit balance. but then you are losing information because your sampling period is now 8 hours, minimum sampling period is 8 hours in a urban area where you have reasonable amount of dust. If you go to a very pristine area, you may not get anything in 8 hours, you have to run it for 24 hours to get something. So, so you see that the measurement protocols are all dependent on what is available for measurement and where you are measuring, and so therefore the standards are defined based on that. Okay. So this is all very interrelated, and each of these will change as we get more and more research and development happening on the instrument side. Somebody says I have an instrument which will measure PM10 for 1000 rupees. Everybody will shift to that now, because you can get wide network of this instrumentation, and that is it. There is no, and if you can prove that it is correct, accurate, then that will be the standard, that will be the new standard now. Okay. So it is in conjunction with what is available currently, technology that is available currently. This is called as a high volume sampler. Now this is a very specific company, that is why it is called as an RSPM, respirable dust sampler. So this is so people design this based on the impactor. The impactor here is a cyclone in this particular instrument, but it does not have to be a cyclone, it can be anything, and it uses a large filter paper which looks like, which is a sheet. You can see that it uses a glass microfiber filter, which is 8 by 10 inches, which is like an A4 size sheet, okay, large filter paper, and you can sample 8 hours and for 1000 liters per minute, so large volume. You can imagine how much of air is going through that. So the amount of particulate it collects is significant. So at the end of it, you weigh it, weigh the filter paper before and after, and you get total mass divided by total volume. So you have total volume. So 1000 liters multiplied by 8 hours into 60 minutes per hour, you get total volume in meter cube, in liters. Right? Total volume is available here, and then whatever is the weight that you collect on the filter paper, you divide by this number, you will get concentrations. Typically the concentrations of PM in air are reported as micrograms per meter cubed. All standards are reported in this unit, microgram, not milligrams per liter, micrograms per meter cube, very small amount. Okay. Now this is the design of this.
So why it is 10 Why that particle greater than 10 mm?
10 microns, sorry, this is not, this is micron. There is a font problem, it is 10 micron. So that depends on the impactor. So in this case, this is the other kind of samplers that is used. In this case, the impactor is here. So this is the air intake, and the impactor is somewhere here or here. No, impactor is in this. There is a pump inside. So this is a PM 2.5 sampler, where you can see that the because of the design of the impactor, the sampling is 24 hours and the flow rate is 16.7. These are related. Because of the impactor works at a certain flow rate, you have to sample for longer. That is one. Second is you are also looking at PM 2.5. The PM 2.5 is less than PM 10, less than or equal to PM 10. You cannot have PM 2.5 greater than PM 10. Yeah. You will be violating mass balance somewhere, or you will have a major error in your this thing. PM 10 includes PM 2.5. Okay, so PM 2.5 should be less than or equal to PM 10. So therefore, whatever you collect in the large PM 10 impactor, PM 2.5 you will have a smaller amount. So you have to sample for longer in order to get something useful. Okay, something that you can measure. So PM 2.5 are all 24-hour sampling intervals measurement. So you cannot do anything. So I cannot get any information on a lower time scale. It is all 1 hour, 1 day average, 24-hour average only. Okay. But this is okay because again depends on the objectives. The way we use this data is we are looking at long time scales. We are saying what happens this year, next year, in 10 years, what will happen if this industry stops polluting, this industry starts polluting, and so on. These kind of things are all what we are discussing when we are looking at ambient sampling, air sampling. We are saying there is a lot of particulate matter in the air. Our first question is who is causing it, what is the cause source of these pollutants, and therefore you also want to see whether this is going to last long. Is this an average? This is not just a single event, or it keeps on happening every day. Okay. So it is related to the way in which the pollutant behaves in the environment. Okay. Okay. So, we only have an average value of this thing that is useful sometimes. We have a next class of this, an extension of this, when we want particle size distribution. Yeah. What we are looking at in the previous two slides is PM10 or PM2.5, one, that is it, done. But what if I want distribution? I want a distribution of particle sizes in different sizes, how much is there in each size. Okay. Then I can decide whether, so this is what is called as a cascade impactor is just an impactor, but you have multiple impactors, one placed after the other. You can see the schematic diagram here that it is going in the first one. There is the first impactor, it goes to this one, and again it goes through, as I mentioned, it goes through the center somewhere, then it goes again outside, then the center again. So, it keeps doing this. In the last stage there is a filter paper. So, here I am not discarding all the intermediate stages, I am taking the intermediate stages and measuring it, how much is there in each stage. So, I am collecting it, so I can as well measure it. So, I can put some filter paper or some medium there and I can do gravimetric measurement there. Okay. Seems this is what it looks like, this is the real impactors and the collection plates and the flow through. So, you can see that there are smaller and smaller, significantly smaller and smaller openings in this row, which allows which changes the trajectory and it also adjusts this. So, this can be one, and you can have slightly larger impactors as is shown on the left side figure. This is called as a cascade impactor, size resolved cascade impactor. You can also have size resolved cascade impactor. This is commercial equipment, you can see this here, it is a small size resolved cascade impactor. People put this and work for 8 hours, they will work, and there is a pump here, you can see there is a pump, and it will give you the filters in each stage will look like this, and you can coarsely define based on the impaction design. You can say 2.5 to 10 microns, 0.18 to 2.5 microns and less than 0.18 microns. So, you can have some classification, broad classifications, and you can see that as the size keeps going down, the amount of particles also is going down. This is very thick, here of course it is very large. So, this indicates that very large amount is less than 0.18 microns, but you can't classify it further, it all gets stuck on the filter paper. This depends on where you are. So, some distributions depends on distribution of particles in that area, it will always not look like this, it will look the reverse sometimes. Large particles will be very big and smaller particles will be very small, and that gives you an indication as to what is the nature of particles. Okay. This seems a very painful thing to do, especially when I have, so this is some of the instruments that is used in, this is the problem. So, when you are a regulatory agency, you really like to know real time information. You would like to know what is going on real time, so that you can focus your energies on fixing where the problem is, which is the biggest source of pollution. This is like an investigation, this is really like a proper investigation where you are looking for clues and you are connecting it with what is the cause of these things. So, the blue line here indicates the real time data and the pink line indicates average. So, I have an 8-hour average, I have this concentration 8-hour average, it's over 125, 130 or something, but I can see that throughout the day the concentration is going up to 300 and coming back down to 50 or 0 all the way, this is possible. So, people are looking for real time monitoring all the time. Okay. So, there are a lot of instruments people have tried to develop to do real time monitoring, and one of the things that people do in the CPCB's monitoring station in regulatory agencies is to do, one of them is called as the beta gauge monitor, beta attenuation monitor. It is a very difficult slide to read, but basically what it looks like is this: there is a roll of filter paper, there is a filter paper, this is rolling here, there is a sample inlet sample, it goes in, sample goes in through here and deposits on the filter. So, there is a small amount. So, for a certain period of time there is some deposition, and then the sample moves to an optical detector. The optical detector sends some light of some wavelength and it measures what is the difference, change in the attenuation. The signal attenuates, it will attenuate more if there are more particles, attenuate less if there, it is like absorption, what we saw, scattering or absorption. Basically, it will look at transmission and it will say if a certain amount of If there is a lot of loss in transmission, it means there are a lot more particles, that is all, simple as that. So, you have to calibrate it against that. The particle mass is calibrated against the transmission, and then you say if this much is the loss in transmission, I am assuming that this is the particle. Because you are already classifying it, see here you are classifying it, you are removing all the, if you are doing PM10, you have a PM10 impactor here. So, what is coming through is PM10. So, you can measure PM10 in real time, and depending on the sensitivity of the transmission loss, I have a minimum sampling time. I will wait there for 10 minutes, 20 minutes, half an hour, 45 minutes, whatever time. Whatever time it takes for me to collect enough material, that will give me sufficient, minimum detection limit has to be determined and the sampling time has to be determined. So, you see all of these things are important in the design of equipment for real time analysis. So, this is one thing that is used in this. There is another equipment called as a microbalance, tapered element oscillating microbalance, which looks basically, it allows for the deposition of particles on a tip which will vibrate, which will oscillate, and based on that they will calculate what is the amount. So, this also it is used every, it is accumulative, which means that the change will incrementally change incrementally. So, it is like putting a small thin film and particles keep depositing and the thin film will bend, and the more bending, which means that more particles. So, you can incrementally say 5 minutes and bending this much, then bends this much. So, you can get distribution as long as you are able to detect that change. In this case, it is changing the detection of the vibration or some force, it's a force measurement or some such thing. Okay. They are all very sophisticated instruments. You can imagine that this is going to be more expensive than your high volume 4 digit balance, obviously. Okay. So, there are other methods of doing real time analysis. Okay. I am going to ask a question at the end of this discussion, and you have to be prepared for that. There are optical methods, which is there is a laser and it is based on scattering principle. There is a particle, light hits it, it scatters, and it is based on the scattering law. The amount of scattering and the angle of scattering depends on the size of the particle. Okay. So, different detectors are kept here. In a full design, there are a lot of detectors that are kept at different angles, and you can find out which is what is the size based on the scattering angle, and you can also measure the composition, concentration of it, count the number of particles. Okay. So, the real time monitor, this will give you data, very good data, it will give you real time data, because it is measuring it as it is going through. Particles are going in and scattering is happening continuously, laser is hitting it and you are getting numbers, you will get numbers like this, and there is a filter at the end of the system which will collect some amount. This is a next level of optical instrument. Okay. So, this is based on scattering. This one, there is another instrument which is based on what is called as time of flight. Okay. This is called as an aerodynamic particle sizer, and as the name suggests, this exactly does what the aerodynamic diameter definition is. It takes the particle and it finds out what is the momentum of the particle, how fast it is moving, a certain size, and then and based on that it calculates what is the size of the particle. So, there are two lasers, it calculates how much time it takes for a particle to go from one place to another place, and it is a very sophisticated equipment called as APS. Okay. This is not an optical method, this is a aerodynamic method. Okay. This is incorrect, this is aerodynamic method. Now, you have these instruments, this is real time. Why would anybody want to use a PM based gravimetric measurement when you have these available? You are getting real time data, you are getting, without much thing, no processing required. It is very easy for students to use it. They will take this thing, put it there, and numbers are coming, and you just have to plug in a USB drive or something and get the data. That is it, done, nothing involved, no work involved. There you have to take a filter paper, weigh it, go and measure it, come after 8 hours, take it out, and you are getting 8-hour average, loss of information. Or in the Cascade impactor you are taking. Why would you want to still do that? One is a very obvious reason. What is the obvious reason? Cost. One, say cost is there, but you may still want to do it. What is the second reason why you may still want to do it?
Maybe sensitivity to see for the chemical composition.
for composition. So, sometimes you want chemical composition and you are getting a lot of material. So, you are looking at composition of the particle, because that composition will give you a lot of clues to where it is coming from. Just getting mass distribution is not enough. Okay. Multiple sources may be giving it, if you get size distribution, it may not be just enough. So, people are always trying to find out the cheapest method of doing it, what we call as source apportionment. We have source apportionment, you can do source apportionment as long as you get a very specific signal for a source. Yeah. But sometimes there is mixed signals, you do not know how to resolve signals. One way of resolving these signals is by using composition, chemical composition. If you have enough information in size distribution, that may be enough for you to make source apportionment, that is fine, that is good. But if you want complete information, you need to get composition, which means you need actual physical mass. That is one reason. The second disclaimer here, this optical method is not measuring aerodynamic diameter, this is measuring a scattering diameter. So, it is a different diameter than what we define as PM10. It may be the same for some particles, but it is likely that it is not. So, you have to be very careful when you are reporting this as PM10 versus something else. You have to make sure that there is a correlation between this and that. So, the only way to do a correlation is you do PM10 using the APS. The APS, this will report the aerodynamic diameter. You can put this versus this. You can see this instrument is much cheaper than this instrument. Obviously, you can see the amount of electronics and amount of this thing involved in it. So, this is always going to be the challenge, and currently we are a lot of groups working on trying to get cheap instrumentation, because one of our goals in freight and transport, as we will see in the next, is to have a wide distribution of measurement. We want atmospheric measurement, and somebody will give you some number and you do not know what it means, as you saw in the quiz paper. You do not know what it means. I say composition is this much, what does it mean? I have no idea. Is it a composition that is arising out of one specific event that happened this afternoon, or is it a continuous thing, or it is periodic? We do not know. Okay. So, all of these are gives information of what is happening in the system, and the system is huge. It can be, system can be city of Chennai, system can be city of Chennai and the surrounding 50 kilometers, it can be the entire state of Tamil Nadu and the Bay of Bengal, it can be the entire southern subcontinent, and the time scales are varying and all that. So, as it is the case with Delhi, we do not know what is the system boundary there because of these kind of things. So, the full information of PM will give a lot of clues to what the problem could be. So, there are further something called ultrafine particulate matter. These are particulate matter which are below, typically it is 300 nanometers and below, 500 nanometers, 300 nanometers, that size range. The reason this is important is a lot of emission coming from vehicles, diesel and other things, particulate matter, are in this size range. It is known, very well known, that it is if you look at the particle size distribution, we have seen that there is something called as a nucleation, condensation and nucleation range, which starts from the lower end, and the higher end of particles are mainly from mechanical breakage, erosion, that kind of stuff, because they are originating from larger particles. This is originating from vapor. So, originating from vapor is combustions processes are all like that. There is a vapor phase at very high temperature and it condenses, it forms a particle. Thermodynamically, it will form the smallest size possible. So, that will be a sphere, it is a very small nanoparticle, and condensation occurs and the particle grows in size depending on how much exposure is there in the system. So, these are all small particles, nanoparticles, and there is a general theory. So, if you look at the trend of PM that is has a health effect, earlier they had no idea, they said all PM is in that, then they said PM10 because PM10 goes into the nose. Then they said PM10 does not go into the lungs, it stays somewhere near the nose and throat, PM2.5 goes into the nose. Now, the theory is further down. When you are going further down, you are already in the nanoparticle range, a few hundred nanoparticles, very difficult to measure. So, how do you measure nanoparticles? Nanoparticles you can't do gravimetry, you have to collect millions and millions of particles and still you are not sure whether you are collecting that size range. Classification is very difficult because classification by aerodynamic method is difficult because that is based on momentum, and the mass of the particle is now gone so much that you can't use momentum as classifier anymore. So, people use what is called as electrical mobility. So, electrical mobility, and the instrument that is used to make is called as a differential mobility analyzer. So, we will just very briefly look at it. I will take few more minutes, we will be done. And this instrument, what it does is, it charges all the particles coming in, but depending on the size of the particle, different charges accumulate on particles, and then there is a flow, and there is a potential difference that is placed across these two. This is a concentric cylinder. In the center there is like a cylinder, small cylinder, and outer there is a bigger cylinder. Between this there is a potential difference. This potential difference will pull particles of a certain charge towards, and plus there is also moving. So, based on the electrical charge and the flow, particle also has an aerodynamic behavior. There is a resultant trajectory as is seen by this red and green dots in this picture here. Okay. So, for a particular size of particle at a particular voltage, you can expect one particular trajectory. If you change the voltage, this trajectory will change. So, what is the instrument has an opening here, a very small opening. Particles of that trajectory which correspond to that will go into this opening and be taken out of the stream. Rest of it will go out. So, you are separate. It's like doing mass spectrometry. You are only giving that one particular size charge, and you are allowing one of them to go through. The rest of them you are taking it out. Okay. So, you are separating it like that. So, you are changing the voltage from one value to another value. So, different particles have different trajectories at different times, and it scans through the entire thing. You only want one particle size, you can fix the voltage and only that particle size will go through. But if you want the full scan, like the mass spectrometry, you change the voltage, and the trajectory will keep changing. Whatever this particle will be here, next voltage will be here, next it will be here, and next then it will go here, then it will go through. So, all particles go through this depending on what is your design. But we still do not have a method of measuring it. So, that method of measurement is called as a condensation particle counter. The small nanoparticles, you do not have a way of counting it yet. So, but you know how to count particles that are in the range of about 0.3 microns, 0.4 microns and all, okay, which is using the scattering instrument, which we already saw, that the limit there is about 0.3, 0.2 microns. So, you allow the nanoparticle to grow to that size. How do you allow it to grow? This particle is coming from here, the sample inlet, particles are coming in here, and it is exposed to a saturated environment of some vapor. So, there is a liquid here, and this is evaporating, and it is condensing on the particle, and you can see that this particle has a residence time in this region, and it grows to a certain size. So, particle of dP1 grows to a particle of dP1c, let us say. So, particle of 10 nanometers will grow to say about 200 nanometers. The particle of 20 nanometers may grow to 300 nanometers and so on. So, there is a correlation between what is coming in and what is going out, because the rest of it is fixed. So, based on that you can calculate the particle size distribution and then back calculate what is the particle size that is coming through. It's a very complicated instrument. This entire thing is called as a scanning mobility particle sizer, or SMPS, very expensive instrument. It costs around 50 lakhs, 60 lakhs as you can imagine, and but it is used a lot in trying to understand what is the distribution of particles all the way from 10 nanometers up to 10 microns. You can do the entire thing in one sweep. So, you will get data that looks like this, you will get all kind of things. Okay, so we will continue the rest of it tomorrow. We are looking at chemical analysis and physical analysis later.